In this lecture, let's review the rules for interpreting condensed formulas in organic chemistry, including converting Lewis structures into condensed formulas and vice versa. Before beginning, let's review the common bonding patterns. I'll refer you to my other lectures on common bonding patterns for elements encountered in organic chemistry. I'll give a brief summary here. Neutral carbon will have 4 bonds. These can be 4 single bonds, 2 single bonds and a double bond, or a single bond and a triple bond. Finally, the halogens, which include fluorine, chlorine, bromine, and iodine, will typically bond only one way, a single bond with the halogen atom having 3 lone pairs. Interestingly, hydrogen, which follows the duet rule, it can only have 2 valence electrons, will also participate in only one single bond, but have 0 lone pairs. Now, let's do some examples. Let's draw the condensed formula for hexane. Hexane is the 6-carbon alkane. We see the 6 carbon atoms in a chain here. This is a straight chain alkane. That means all 6 carbons are bonded in a single chain. They are surrounded by hydrogens. And to write the condensed formula, what we want to do is group these atoms together. Of course, in organic chemistry, some of these larger molecules, their Lewis structures can be more complicated. There's more atoms to keep track of. There's more electrons to keep track of. So writing condensed formulas makes this a little easier to look at. To write condensed formulas, what we'll do is we'll group these atoms together. So at the end here, we have a carbon atom that starts the chain. And what we'll do is we'll write the atoms that are bonded to this carbon atom. We'll write those atoms after the carbon atom. So after the carbon atom, we have 3 hydrogen atoms. And then in the middle of the chain, you'll see a lot of these in organic chemistry. You have these CH2 groups. These are called methylene groups. So the next carbon in the chain will be followed by 2 hydrogens. That's this first methylene group. And then there are 3 more, for a total of 4. And then at the end, we have this final CH3. This is the condensed formula for hexane. Interestingly, we can simplify this even further. So where we see we have these 4 methylene groups, we can actually condense this even further. So here's the CH3 at the end. Then what we can do is write CH2. We can put this in parentheses and write a 4 on the outside. And so this tells the reader that in this chain, there are these 4 methylene groups. And we'll close it with the CH3. In this example, let's start with a condensed formula and convert this to a Lewis structure. Of course, in the Lewis structure, we want to show all of the pairs of electrons in the form of bonds or lone pairs. In this case, I'm doing another hydrocarbon, so nothing but carbon and hydrogen here. And just like we saw with the condensed formulas will just give us the grouping of atoms. Now, it's important to know the common bonding patterns here. So we're looking at this carbon chain. So here's this first carbon, and it's bonded to this next carbon. We know from the common bonding patterns that hydrogen cannot be in the middle of a chain. It cannot have more than one bond. So hydrogens are always on the outside. So this carbon is bonded to these 3 carbon methylene groups and then the carbon at the end. If you know the common bonding patterns, you know to satisfy the octet rule, we'll put these 3 bonds, these 3 hydrogens on this carbon on the outside, this terminal carbon. The methylene groups in the middle of the chain have these 2 hydrogens, so satisfy the octet rule here. And then, of course, at the end. In general chemistry, we would want to count the valence electrons and make sure that all the valence electrons are present. Of course, in organic chemistry, when you're dealing with molecules that are starting to get pretty long, these chains are getting longer, counting the total valence electrons becomes somewhat cumbersome. So what we want to do here is just make sure that the octet rule is satisfied for all the carbons. Carbon in each case here has 4 bonds, so that's good. Hydrogen participates in the duet rule. It forms 1 bond, and that's it. Let's convert this Lewis structure into a condensed formula. So you follow this carbon chain right here, and you recognize something interesting is happening here. It's not a straight chain alkane. It's actually branching off. So at this carbon here, you have a carbon group going up and then 2 carbons going to the right here. So this is called a branched alkane. And what I'll do is I'll follow the longest carbon chain here. So there's a 5 carbon chain here, and we can think of this 1 carbon as being branched off. And for naming purposes, right, this is an alkyl group. And so there's a special rule here that we'll have to follow. But let's start writing the condensed formula. Let's start from left to right. So we'll go ahead and start grouping our atoms. At the end of this carbon chain, we have this CH3 group, followed by this methylene group, CH2. And then we have the middle carbon. This middle carbon is bonded to a hydrogen, and it's also bonded to the CH3 group. Whenever you have these alkyl groups that are branching off, we need to put these groups in parentheses. The significance here is that the parentheses tells us that this group is not part of this 5 carbon chain, but rather this group is bonded to that previous carbon. So remember the rule. We see a carbon, and what follows the carbon is what's bonded to it. So this carbon is bonded to this hydrogen, that's this one right here, and it's bonded to this methyl group or this alkyl group, the CH3 right here. And then we can continue on with the chain. So here's the CH2. That's this group right here. And then at the end, the CH3. Let's convert this condensed formula into the Lewis structure. So here are the groups. We'll start with the CH3. And after the CH3, this carbon is now bonded to this next carbon, this next methylene group. And then this carbon is bonded to this next carbon, the 3rd carbon in the chain. Notice in parentheses, there are 2 CH3 groups. The significance of the parentheses means that these carbons are bonded to the previous carbon. So this carbon is bonded to these two CH3 groups. I'll draw one on top. I'll draw one on the bottom. Yeah, you have to give yourself a little bit of room here. And so these groups, I'll draw a star here. These are the two CH3 groups. And we'll continue on with the chain. So this carbon is also bonded to the CH2 group. And then at the end, we have the CH3 group. In this example, you notice there's a condensed formula. If you look at this carbon here, you'll notice that there are groups in parentheses on the right, but there's also groups in parentheses on the left. So what happens here is that we can look at these groups in parentheses and say that these three groups are bonded to this next carbon right here. Again, we just want to satisfy the octet rule for all these carbon atoms. So for example, if I start with this carbon right here, what I'll do is I'll add these three CH3 groups to it. So let's start there. You definitely want to give yourself a little bit of space here. And then add those three hydrogens to each one of those carbons. So here are the three CH3 groups. I'll go ahead and put a little star here. That way you can see those three carbons. I'll put a blue star here to label this first carbon. And then we can continue. So this carbon needs one more bond to satisfy the octet rule. And so right here we see this group here, the CH2. These are methylene groups. And there's two of them. There's a two on the outside of the parentheses. So we'll just go ahead and continue the chain here. So now this carbon has its octet full. Here's the first CH2. Here's the second. And then we'll close up this carbon. We'll complete the octet by adding the CH3 at the end. Let's draw another Lewis structure from a condensed formula. Now this one's interesting. Watch here. Here's a CH3. And this CH3 group is bonded to the methylene group, this CH2. And then we continue the chain. This carbon is bonded to this carbon. After this carbon, we have a hydrogen. So that means that this hydrogen is bonded to the previous carbon. We've seen that before. And that's it. Notice that this carbon is now bonded to the next carbon in the chain. And that carbon is bonded to one hydrogen. And then we continue the chain with a CH3, and then that's the end of the chain. So we're finished including all of the atoms, but if you look carefully, there's something missing here. If you remember the common bonding patterns, neutral carbons should have 4 bonds. This carbon has 4 bonds. This carbon has 4 bonds. The carbon at the end has 4 bonds. But the carbons here only have 3 bonds each. Now in general chemistry, we would typically count all of the valence electrons and then go in and make sure that we account for all of the valence electrons. In organic chemistry, these molecules can get pretty big. There could be many electrons. The simplest thing to do is just to follow the bonding patterns. Each one of these carbons only has 3 bonds. We want to give it a 4th bond. Remember, neutral carbon has 4 bonds. The simplest thing to do is just give it the double bond. So here's a carbon-carbon double bond. This is called an alkene. And we'll close with this example. Again, let's convert a condensed formula to a Lewis structure. We'll start at the end with these hydrogens bonded to that first carbon. We see 3 methylene groups. So just continuing the chain here. We notice that there's another carbon in the chain, and then it's bonded to that next carbon in the chain, and then the CH3 at the end. Very similar to our last example, we count the valence electrons around each carbon, or you look at the bonding pattern. Neutral carbon should have 4 bonds. Each one of these carbons has 4 bonds, and the carbon at the end has the 4 bonds. But these 2 carbons each only have 2 bonds. So the simplest way to give each carbon 4 bonds is just to draw that triple bond. And this is called an alkyne. I want to do at least one example where we highlight the alkyl halide, and that's the halide right here. It's a bromine. Halides are these halogens that are bonded to these hydrocarbon chains or bonded to these carbons. Fluorine, chlorine, and iodine are the other halides. And so let's draw the Lewis structure here. We'll start with the CH3 group at the end. This carbon atom is bonded to the second carbon in the chain. And then we have the hydrogen and the bromine. Of course, the common bonding patterns are these hydrogens can only form 1 bond, but also the halogens only form 1 bond. And so this bromine is not part of the chain, but rather bonded to this previous carbon. Let's not forget in the Lewis structures to include those lone pairs of electrons around the bromine. There's the CH2, and then at the end, we have the CH3.